Hello, my name is Ihor Kozakevych, and I would like to present you our work on the topic Predictive Control of Induction Motor Drive. Recently, the vector control system and the direct torque control system have proved to be the main control systems for AC electric drives. The advantages of the latter include the ability to work without an angular speed sensor on the shaft, simple structure, and high dynamic quality control. At the same time, the main disadvantages of this system are the high level of torque ripple, which becomes especially sensitive when working at low speed, as well as the presence of a variable switching frequency of power switches. A number of researchers' work in the field of automatic electric drive are devoted to solving these problems. Among such systems, the system of predictive torque control deserves special attention, which can be considered as an alternative to the system of direct torque control for electric drives with induction motors. To use such a system, it is necessary to use discrete models of the power converter and induction motor, and the values of stator flux and torque are considered as control variables of the system. The use of the mentioned discrete models allows to estimate and predict the values of stator flux linkage and torque, and further, on the basis of these predictions, the cost function is calculated, which allows to select the optimal control effect for the next discrete interval of the system. The structure of the electric drive using the direct torque control system is shown in this slide. In such a system, the induction motor is powered by a voltage-fed inverter. The task of the system is to provide the ability to independently control the values of the stator flux and motor torque by selecting an appropriate states of the inverter. As you know, a voltage-fed inverter is able to create 6 non-zero space voltage vectors, shifted by 60 degrees, as well as 2 zero voltage vectors. The system uses relay hysteresis torque and flux controllers, which allows to provide high dynamic control of the electric drive system. The principle of direct torque control can be explained by considering the mathematical expression for the electromagnetic torque in the following notation. It is believed that the stator flux vector reacts less inertially to the voltage applied to the motor windings, because the rotor time constant is significant. For simplicity, it is assumed that at one discrete interval of the system, the vector of flux linkage of the rotor is stationary. Therefore, the rotation of the stator flux vector in the direction of rotation leads to an increase in the value of the angle theta and increases the torque. If the space voltage vector applied by the inverter causes the flux vector to rotate in the direction of convergence with the rotor flux vector, which will reduce the angle theta, and torque generated by the motor will decrease. Thus, the use of direct torque control system allows independent control of torque and stator flux linkage. The selection of the appropriate voltage vector and the state of the inverter switches is carried out using the table of optimal switching, which is presented in the table. Predictive control systems for converters and electric drives are currently being actively developed. The principle of predictive control is to predict further changes in the system state variables using a mathematical model of the system. In the next step, a certain optimization principle is used to compare possible options for changing the state of the system with each other in order to identify the most profitable in terms of achieving the ultimate goal of control. It is necessary to use a discrete model of the control object, which will allow you to predict changes in the state variables. The equations of electrical equilibrium of the stator circuit of the motor in the stationary frame of the reference alpha beta have the following form. Convert previous equation into a discrete form using Euler's method. The obtained equation allows to calculate the flux linkage of the stator which refers to the discrete step n+1, based on the value of the flux linkage of the stator, which refers to the previous discrete step n. The components of the flux vectors of the stator and rotor can be written through the appropriate inductances and currents. Since the rotor current is not measurable value for motors with a squirrel cage rotor, we get rid of its use through the combination of previous equations. The dynamics of change of the components of the flux coupling vector of the rotor can be described by the following dependencies. Using the Euler's method, the prediction of stator current can be performed in the accordance with the following dependencies. Prediction of the value of the electromagnetic torque can be obtained using the predictive values of the stator flux and stator current. The cost function is composed using the deviation of the torque value from the specified value and the deviation of the modulus of the flux linkage vector from the corresponding rated level. The structure of the system of predictive torque control of an induction motor is presented in the slide. By analogy with the previous system, the torque reference signal is formed by the PI controller, and the magnitude of the stator flux linkage when operated at the speed lower than the rated, usually set at the rated level, and attenuated when switching to higher than rated. Based on the measured values of motor current and voltage, the values of the torque and flux linkage of the stator are estimated because the direct measurement of these values is difficult to implement. Based on the obtained equations, the values of motor torque and stator flux coupling are predicted by applying each of the 8 possible voltage vectors generated by the voltage inverter. We get 8 values of the cost function, from which the minimum value is selected, and in the next interval of discreteness of the system, the inverter applies to the motor a vector with a number corresponding to the obtained minimum value of the cost function. A mathematical model in the Matlab Simulink environment was developed to analyze the predictive torque control system of an induction motor. The parameters of the motor used in the simulation are given in the table. The slide shows a comparison of motor torques when using direct torque control and predictive torque control in steady-state operation. The graphs show that the use of predictive control reduces the level of torque ripple. The slide shows the shape of current flowing through the stator windings. They show that the use of predictive control reduces the distortion of the current shape, increasing the energy efficiency of electromechanical equipment. The slide shows the response of the system to changes in load torque. The graphs show that the predictive control system has a higher dynamic. The work considers the system of direct torque control and the predictive torque control system of an induction motor. To compare the two systems, mathematical modeling was performed in Matlab Simulink environment, which showed that the use of predictive control reduces the level of torque ripple and improves the dynamic control of the electric drive.